Okay, we're on the clock. So, just quickly reminders of things that are going on this week. So we don't have lab this week because we're doing the exam on Thursday. You have Mastering Chemistry for Chapter 2 due Wednesday night. Tomorrow we'll work all the problems at the end of Chapter 2. So once I'll give you examples of the ones at the end of the chapter. And we'll probably do part of Chapter 3 as a lecture since we're not doing lab. So probably spend about an hour lecturing. The other half we'll spend working the problems. Then you also will have the Chapter 3 assignment, which is a really, really short one. So those are the things you need to be starting to prepare for the exam. That's the thing I encourage you to do. So that's going to vary for every one of you, how much time and effort you're going to need to put into it. A lot of this is material you've seen before in other science classes. If you had high school chemistry, there's probably not that much new at this point. We're going to get the new stuff, but do what you need to do to prepare. Right, so continuing in the Chapter 3 materials. So the thing that we're talking about are Chapter 2 materials. Finish the chapter up. The thing we're talking about is how we can look at atoms and figure out what their mass is. So when we look at the average mass of an element, we call that the atomic mass. It's also called the atomic weight. And it is related to every element and the isotopes that exist for that element. Now, we talked about earlier in the chapter that different elements have isotopes. And the isotopes are where you have a variation of the numbers of neutrons. The protons stay the same. You just vary in the number of neutrons. Because the neutrons have mass associated with them, that varies, the mass varies with the different composition of how many of what percentage of the isotopes are present. So what we do when we report the average mass, we have to take all the isotopes into consideration, and we report a weighted average according to the natural abundance of each isotope. So what that means, if you look at the common elements or some of the common species, if we look at like carbon, we would have to take into account that most of the carbon is carbon-12, but sometimes there's a heavier form of carbon. It's a carbon-13. It's roughly 1% of the time, a little bit less than 1%, and very, very rarely is the form called carbon-14. And I'm just going to put trace. It's a very low percentage, and we'll talk about that trace in just a little bit. Okay? It's the larger percentages that make a contribution. So another one that's a common one that's around us, and it's got two isotopes. Maybe you put some on your food this weekend. It's some form of chlorine. If you put salt on anything that you ate. Chlorine exists in two major isotopes. Chlorine-35 is the most abundant. It's 77.7 or 75.77%, and it's got a mass. If we look at that particular isotope of the chlorine 35 isotope, it weighs 34.97. Now, the AMU stands for atomic mass units, and we'll talk about what an AMU is as we go just a little bit further. Originally, Dalton said this mass unit was set up on a hydrogen atom. The problem is he didn't know that hydrogen atoms varied. He thought hydrogen was the lightest element, so he compared everything to hydrogen. So today we've changed it just a little bit. The other isotope that exists for chlorine is the chlorine-37, and 24.23% of the atoms are in that form. And it has a mass of almost 37. It's 36.97 AMU. So what we do when we calculate the actual atomic mass, we need to find out what the weighted average is for all the isotopes that are present. In this case, it's just the two, chlorine-37 and chlorine-35. So to get the weighted average, what we do is we take the percentages and we convert those into a decimal equivalent form. So those percentages are what we call the natural abundance. So for the starting with the chlorine-37, the 24.23% as a decimal equivalent is 0.2423. Okay, times its mass, so its mass was the 36.97, and we find out its contribution is 8.9578. And we do a similar thing for the chlorine 35. So the chlorine 35 is 75.77, and we convert that to a decimal equivalent. It's 0.7577 times its mass in AMUs. Its contribution is 26.4968. So now what we do to find out the weighted average is we take those fractions and we add them together. So the pieces add together to make the whole. So I add together both of those masses and I get what we see in the periodic table. The weighted average of the isotopes is the 35.45. So if I look at chlorine in the periodic table, I see the 35.45. Now the thing to understand is there's no atom that weighs 35.45. Okay, you've got either atoms that weigh right at 35 or right at 37, but that number that's in the middle is the weighted average. Now that weighted average becomes important for me when I want to start weighing atoms out because it gives me the best idea to represent. If I want to count atoms, I need to use this average mass. So the formula that we use to describe that with is this guy. This is the one that you'll get on the equation sheet. You might have looked at that. Again, I'll remind you, I encourage you to print that equation sheet out with a study guide and use that to start working problems with to review for the exam, because that's the exact equation sheet you're going to get on the test. But what we did is we're summing together simply the fraction of the isotope times the mass of each isotope. And this means sum or add together. Okay, so if it were in the case of the previous one we did, it would have been the chlorine 35's fraction plus the mass of chlorine 35 plus the chlorine 36 plus its fraction. If we were to do the carbon, we would say the fraction of carbon 12. Okay, so the fraction of carbon 13 and the fraction of carbon 14. Different elements differ on the number of isotopes. There's only a few that only have a couple. Now, how do we know what isotopes exist? We have an instrument called a mass spectrometer. We actually have two different mass spectrometers at Southeastern, but they're common in chemistry labs. They're pretty expensive pieces of equipment. When you take upper level science classes or chemistry classes, you'll get to utilize one or at least the data from them. But they're about $100,000 an instrument. Some are getting a little bit cheaper today, but what they have the capability of doing is they can determine the mass of individual atoms and their percent abundance. Anybody that's went through an airport has had some type of mass spectrometer. Probably if you went through screening, has anybody went through a screening where you had to hold your arms up and blew the little puffs of air at you? Okay, what it's doing is looking for explosives and drugs. It's looking for particles of drugs or explosives that are knocked loose. It runs them through this mass spectrometer very quickly, and it measures, is there anything that has those masses that they know to look for, those signature spectras. And if it does, the alarms go off and you're fixing to get patted down and searched in ways you don't want to be searched. Okay. But if we were to look at something like chlorine in the mass spectrometer, it doesn't see chlorine by itself because chlorine exists as those two different isotopes, chlorine 35 and chlorine 37. And it would see a signal at each mass. It measures mass and intensity, and it would see the two things at a ratio of about 1 to 3. Okay, so 1 to 3 ratio between the two. And that's what we expect to see. If we went back and looked at chlorine, we saw the percentages were about 75% and about 24%. It's about a 3-to-1 ratio. Okay? So the mass spectrometer gives us the capability to know what those actual abundances are in nature. Once we do this we know what the ratios are, we can calculate them. What we have today are more and more precise instruments that allow us to know this with more decimal places. Most of the elements we know these numbers out to much more than the 2 decimal places that are in this abbreviated periodic table. Some elements we know out to 7 and 8, and a few 9 decimal places. One of the common things that we do with looking at isotopes, maybe you've heard this term, is something called radiocarbon dating. So let me insert a blank page here. So with carbon dating, we're looking at the carbon isotopes that exist. So carbon, when it gets in the upper atmosphere in CO2, it gets bombarded by nuclear particles, okay, so high radiation, and it converts a certain ratio of the carbon to the radioactive form of carbon that involves the C14. So it's a C14 CO2, carbon dioxide. Okay, so all this occurs in upper atmosphere. So above, way at the top of the clouds. So what happens as soon as this C14, as it starts to decompose, starts to radioactively decay, and the amount of C14 starts to decrease as a function of time. So decreases with time. So whenever you do radiocarbon dating, what you're looking at is the ratio. You'll take any sample that has carbon in it, so carbon-based material. You'll take and burn that, and you'll capture off the CO2. So whenever you burn a carbon-based material, combustion yields CO2 and water. We'll take that CO2, it's trapped, and then we'll analyze the CO2, so into a mass spec, MS, mass spectrometer, and then what it does is it tells us the ratio of the CO2 that exists that is C12, which is the most abundant, and it weighs 44, to the ratio of the C13, which is the rarer of the two, so it's about 100-to-1 ratio. But occasionally it weighs 44. There's one of these slightly radioactive ones, and the scale is not correct at all, because this is at the 1/10,000th to 100,000th, depending on how decayed it is. So this one's going to be at 46. It's the C14 CO2. Now the thing is that the ratio of the C13 CO2 to C14 CO2 is fixed as long as the material is in the atmosphere and it can exchange and undergo this process. So as long as it can get up into the upper atmosphere, the CO2 is floating around, that ratio becomes fixed. When something the carbon becomes captured, becomes part of a tree, part of a plant, part of fossil fuels, whatever it is, gets absorbed into a rock, what happens is that C14 signal starts to decay. And as the C14 gets smaller and smaller and smaller, we can measure that. So when we're looking at this ratio, we're doing radiocarbon dating, simply looking at the ratio of those two isotopes. We can tell within about 5% accuracy has something been out of the atmosphere 500 years versus 5,000 years versus 500,000 years versus 5 million years. And it's not perfect, and one of the biggest problems with it, especially with historical art that's been something that's been handled by human hands recently, is the possibility of contamination. So it's not foolproof. If there's anything that's been recent handling it, something's been passed around and looked at, it's an artifact of interest, it can be contaminated with more recent forms of carbon that can skew the results, but still it's our best indication to determine age of something. So here's kind of what the mass spectrometer looks like and the principle behind it. It's really an engineering feat, but what it does is take an atom and converts it into a charged atom by converting or knocking electrons off of it. So if it were something like carbon, it would take a carbon sample of the carbon dioxide molecule, and it would knock an electron off of it to produce the carbon dioxide cation, positively charged. And now that it's positively charged, it can manipulate that charged ion with an electric field. It gives it some velocity, and it runs down here, and it runs into some magnets. And when it hits the magnets, depending on the mass that it has, it either has the correct energy to go straight, and maybe it's detected, And if it's the lighter form of carbon, it gets bent more because it doesn't have as much kinetic energy, or if it's something heavier, it gets bent less. It goes to a different spot. So that's the way the mass spectrometer works in the simplest view. It's actually much more complicated than in the real world, but that's the basis of how we did this instrument. And if you take more advanced classes, we'll teach you all about that. All right. The reason that we're interested in it is we want to know how we can count atoms. When we want to know how many atoms are in a sample, we can't individually look at it and say 1 atom, 2 atoms, 3 atoms, 4 atoms. We have to be able to take some kind of conversion to go from mass to the number of atoms, or vice versa, or number of atoms to mass. So that's the conversion we want to do. We want to know how many atoms are present in a given mass of material. And the reason that's critical for us is what happens between atoms. What everybody learned is that it happens at the atomic level, between particles. One atom reacts with another atom. One molecule reacts with another molecule. So it's critical that we know the number of atoms when we start talking about chemical systems. And the way that we do that is we count them by weighing them. So what is our process that we use? Well, first I'm going to give you a clicker question. So going back to what I showed you about mass spectras. Okay, so I want you to look at the mass spectrum here for gallium in the periodic table. So it's open now. And the fact that the hint I can tell you is that look at the ratios between the two different isotopes that exist of gallium. Get that out of the way. Okay, so you'll see the 69 is a little bit higher than the 71. Based on that, what does that tell you about those isotopes? You can figure that out. Okay, 16 of you. 20? Get more? Okay, I think that's everybody at 24. All right, so let's see how we voted. So most of you thought it was choice C. Okay, indeed, that's what it tells us. The fact that there are more atoms that weigh 69 means if I look at the weighted average between these two, this is going to skew the average a little bit in this direction. And if I look at the periodic table in gallium, find gallium in the periodic table, it's element 31, I see it's slightly less than 70, 70.3. And the reason it's at 70.3 instead of 70 evenly is because there's more atoms that exist in that lighter form. Okay? And whenever we look at the periodic table and the elements, and the masses that we see, sometimes we see something that's a number in the middle. Okay, so something like the chlorine that we talked about, something like germanium, so it's got a 0.6, iodide's a 0.7, xenon's a 0.3. Those things means that there's some combination of isotopes. Whenever you see something that's very close to the integer value, like oxygen 16, the most common isotope for oxygen is oxygen 16, and it represents 99.5% of all the oxygen. Right? The same with fluorine. Fluorine doesn't have any isotopes. Fluorine exists only as fluorine 19. The ones that are close to the whole number means that there's one predominant isotope that exists. If it's not, it'll be some combination of. And we're going to learn about how those combinations exist. Right, so I wanted to give you a hint on how to do one of these mastering chemistry problems. I'm not going to work it out completely for you, but I want to give you the hint to do it. So it says silver has two naturally occurring isotopes, silver 107 and 109. and it gives you the mass of each isotope exactly. Okay, so what it wants us to do now is calculate the abundance of those two things. So we're going to try to figure out how to set up the equations. We can do it with that. I want to know what percentage is in silver. Silver is Ag. Okay, so Ag 107 versus Ag 109. Okay, how much is in each percentage? Which form? Is it 20%, 80%? Just what are the numbers? So the thing that I can use as my hint is I can go and use that formula that I have. So I can look in the periodic table and find silver. And silver's here. It weighs 107.9. And I know that that's the weighted average. Okay, and I'm going to call it times the, what I'm going to call is X, the percentage for the 107, or the decimal equivalent for the 107. Okay, so it's going to be the decimal equivalent of it. And I'm going to call Y is the decimal equivalent for the 109. So I know the weighted average is going to be whatever the value of X is times the mass of the 107, which is 106.905, plus whatever Y is, okay, which is the decimal or the value for, so Y is the decimal equivalent to the percentage for 109 isotope, times its mass, which is 108.9048. And in the back of the book, there's a table that probably gives you this to more decimal places. It'll actually help you get a better number if you don't have a periodic table as limited as this one. So you've got a more extended answer to this. So I'd look up another decimal place or two for this. Okay, so I've got an equation that's got two variables in it, X and Y. Can I solve that directly? If you got two unknowns, can you solve that with one equation? What's it take to be able to solve that mathematically? Have to have a second equation. Okay, the number of equations has to equal the number of unknowns of the variables in the system. Here my variables are X and Y. Does anybody, can you think of a relationship between X and Y? Okay, and let's go back and look at the, I'm going to go back a little bit and let's look at the X and Y for the chlorine. Okay, so here was our chlorine problem that we did. Okay, here were the X and the Y for chlorine. What did they add up to be? If I took this percentage,
I'm going to add to be 100.
Exactly. The pieces have to equal the whole. They're 100%, or in this case, they add up to, in the decimal equivalents, they add up to exactly 1. That becomes the other equation, or the other variable to solve for. Okay, so now I'm going to go back to our, plug another piece into it. So now the second equation is X plus Y equals 1. That's a simple two-equation algebra problem. Okay, you've all had some algebra to get here. Or you scored well enough on the math ACT, you can put those two equations together and find out what X is. Then once you find out what X is or Y, you substitute it back into your solution, back into the bottom equation, and you find out what the other one is. Okay, so that's the way you set that up. So I'm doing everything there but doing the math for you. But that one's a little trickier one. It's a critical thinking problem. As we get further along, I'm going to expect you to start doing those on your own, but I'm giving you the hint on that guy. Okay. So here's the different problem. So now I want you to tell me what the mass is for the lithium isotope. Okay. So you're working it. You can ask a neighbor. Got a couple of minutes. I give you the formula. So I want to know what the percentages is. The lithium isotope. It's the same problem I just put on the board. See if you can work through that. Try to set the math up. You need the, sorry, this is working it backwards. You need the periodic table to see. So you need the mass of lithium, which is over here on the far right-hand side. Its average mass is 6.941. So you could set the math up and solve it. That's one way to do it. Or you could figure out which one of those answers gives you the right solution. Again, this is a group problem. You can ask your neighbor. You understand what to do? See how they're going to do it.
They know that. They do.
You need to try to figure out what percentage is in the lithium-6, what percentage is lithium-7. Yep. Exactly.
Like that.
A lot of puzzled looks.
So our row has no idea.
Okay.
We have it down to B or D. Yeah, so we don't know what to do.
Okay. Well, your check you can do is go back and plug it into that equation. So if you think it's B or D, so if you put 16.6% as the decimal equivalent, so it'd be 0.166 times the mass of lithium-6 plus the decimal equivalent for lithium-7 times its mass. Those should add together to be the mass in the periodic table. It's a way you can check and see if you got the right one or not. That's your check. If you don't know how to solve it the long way, you can do process of elimination. One of the four is correct.
Yeah.
Pretty good.
Break that. This is 6.9.
So the same, you do the same thing I did with the chlorine a second ago, chlorine 35 and chlorine 37.
It's 9. Instead of like 8 or 7. See. See. Well, that's the reasoning of it. I know I got the.
All we can do is I got 5.
All right, you have, give me 40 seconds. If you got no idea, you got a 25% chance of guessing the right answer.
Well, I think it's D there.
Yeah.
Oh, it's 0.7.
All right. 5 seconds, put a guess in.
Oh, no. Oh, no.
It says not an option, please try. I put D.
Okay, well, let's see how we varied here. All right, everybody thinks it's D. We're going to find out.
I hope it's D.
So that was the big answer. So let's talk about how you would, we're going to work through the problem and then we're going to do the check. So what I'm going to do is define my variables first, who's who. So first thing I'm going to do is I'm going to call the decimal equivalent for the lithium 6X, the value for the lithium 7 is Y. So I can look up the mass, and I know the mass is 6.941. That's going to equal the percentage decimal equivalent for lithium 6, so times 6.05 plus Y times 7.016. And then I know the other thing is the summation of the two. On all these cases, if you add them together, they're 100%. So X plus Y equals 1. So the way I'm going to work this is solve one in terms of the other. So I'm going to rearrange this equation to say that Y equals 1 minus X. And now I'm going to substitute that into the equation for Y. And then I'm going to have the equation on the top only in terms of X. So I substitute that in. Back to blue. Okay, so 6.941 equals, so I'm going to multiply these two together. I've got 6.015 times X plus, for Y, I've got 1 minus X times 7.016. So now I'm going to take and multiply this term to both. So I've got equals 6.015X plus 7.016 less 7.016X. Now I combine my X terms, and then I've got to get both of these. I've got to get X's on one side, numbers on the other. So I'm going to take this one and put it on this side. So I take the 6.941 and I subtract the 7.016 from it. 6.941 less 7.016. And I've got on the right hand side a negative, or left hand side negative 0.075. Okay, so that got rid of this term and this term. Combine those. What I have left on the right hand side, I've got this number of X and this number of X. So I add those together. Keep in mind this one's negative, and it's the larger term, so I'm going to have a negative answer out of it. I get a negative 1.001X. Okay, my negatives cancel out, so negative and negative make a positive. So to isolate X, I divide both sides of 1.001. And that tells me that X is equal to 0.075. And the decimal equivalent converted to a percentage tells me that it's 7.5%. Okay, 7.5%. Looks good for most of you because that's D. Okay. All right. But what we found was X, and X was, yep, that's the lithium-6, so that's right. And if I were to take and put it in the equation, I know that the two things have to add to 100. So 100 less the 7.5% equals the other fraction, 92.5%. That's that guy. Okay, so that's how you solve the algebra to do it. Let me show you the cheat way you could do it. You know it's one of those four possibilities. So if you weren't for sure which one you could do, which one it was, and you can't remember how to do the long way, the cheap shortcut you could do would be say that you'd have to try it on every one of them. Plus and when I plug in the percentages into this equation, only one of the answers comes up with that value, the 6.941, and it's D. Okay, so that's the check you could, if you think you've done it right mathematically, this is the check you can always do at the bottom to make sure that you did do it right. So when you come up with the percentages, this is the way you check it. If you're still clueless about it, you need to really start investing some time looking over the notes and reading the chat. Because all this stuff's explained out in great detail with a lot of examples in the textbook. And I'll just tell you, I have 100% expectation you're reading the textbook as you come into class. That's what you do to survive in a majors course. Okay. So let's continue. So when we talk about counting things, we need a quantity or a measure of something. So what we use is the term is the chemist's dozen is a mole. So when we count things in terms of atoms, the number of atoms that we have is extraordinarily large. So we use, there's a dozen of something, is 12. A gross of something, even though you may not have heard gross much, is 144. It's just an amount. Well, the term that we use is a mole for chemistry. And a mole is abbreviated MOL. You drop the E off of it. Not much of an abbreviation in my opinion. But what it is an exact ratio of the number of particles, atoms, or molecules. So it can either be atoms, ions, or molecules per mole. And that number has a particular name. We call it Avogadro's number. All right, it's 6.02214 times 10 to the 23rd. Now this is the reason we want to use scientific notation in calculators. You don't want to write some 23 spacing zeros at the end of something. Okay? You've got to have a calculator you can do scientific notation with. And typically when I do a calculation, we don't need to know the last couple of digits. We don't have to know it to that accuracy. We'll use 6.022 times 10 to the 23rd is the form that we'll use. So particles per 1 mole. That becomes our conversion factor. That's known as Avogadro's number. I'll give it to you. Most of the tests will do, but as a chemist, that's something that's just going to get tattooed in your brain. Okay? Because we'll use that number in every chemistry class that you'll use from now on, because it's a way we relate the amount of something. So what does the mole really tell us about material? Okay, this extremely large number. First thing you need to understand is it's just a way of representing how many of something. If we think of a mole of marbles, This is one of the things that's hard for us to get a grip on because that's such an extraordinarily large number. You could have, it could be anything that you're describing. You could have a mole of marbles, a mole of sand grains that's got that number of grains of sand. It could be anything that you wanted to count. And we can do that same type of thing with applying it to atoms, ions, or molecules as well. The thing is that it's such a large number. This is kind of a slide to help you realize how big that is. So if you had 1 mole of marbles, okay, that Avogadro's number, and if you stacked them together as tightly as you could, half-inch marbles, it would cover the entire United States 70 miles deep. It's a number of particles. It's just hard for us. We're not used to dealing with anything 10 to the 23rd. We talk about what's the population of the Earth, the number of living people. Anybody know?
8 billion.
Okay, about 8 billion. That's a 10 to the 9th. Okay? Population of Oklahoma, 3 million, 10 to the 6th. This is hard for us to even to visualize at the end of the 23rd. It's just such a large number. Now the problem is that atoms are so small that there's that many of them in almost the smallest amount of material that we can conceive. Okay, so that's where we've got to take now and shrink down to the size at which atoms and molecules exist. So that's what I'm trying to do. Imagine that now, shrinking it down into, if you look at want to think about this visualization that exists, if I had 18 grams of water, it has that many molecules of water in it, Avogadro's number, which is 18 grams of water. It's a drink, easily. It's 18 mils. It's just hard for us to get that in our mind, but we just have to realize it's a way of counting. So what does this number mean when we think about it at a more specific level? Well, it gives us a way of relating back to the mass of a particular substance. So if we look at 1 mole of carbon-12, because carbon-12 weighs exactly 12, that 1 mole of it weighs exactly 12 grams. So 1 mole of any substance weighs the mass of the periodic table. 1 mole of hydrogen weighs 1.008. 1 mole of aluminum weighs 26.98. 1 mole of zinc weighs 65.39. Any element in the periodic table, 1 mole of it represents that weight in grams. So carbon 12 grams of it exactly is 1 mole, which is Avogadro's number of atoms. And anytime I know these relationships, these can become conversion factors. So if I know mass in a calculation, if I could measure mass on the balance, the same way that you measured mass last week doing your density, I don't know where that C came from. If I could take mass, I could take this relationship of the number of grams of material to the number of atoms, and I could convert it into the number of atoms. And that's exactly what I want to do. Is I want to convert from something I can measure to something I can't count. So it's a conversion factor for us, and that's what it becomes. Now I'll just give you a brief history on why they chose these particular numbers. Originally they said, Dalton said hydrogen is equal to 1 atomic mass unit, the lightest element. And that's what they went with first. But Dalton didn't realize that hydrogen exists in multiple forms. There's hydrogen 1, there's hydrogen 2, which we call deuterium, and there's a very heavy hydrogen called hydrogen 3, which is called tritium. If you're going to do a comparison to something, your reference has to be fixed. So when they realized that isotopes exist and realized we can't just say a hydrogen atom because hydrogen atoms can vary from atom to atom, they had realized they had to choose a particular isotope. At that time, they made the decision to use carbon-12, and based on that, carbon-12 became the reference for what everything else is measured with. And the number is that 1/12 of the mass of a carbon-12 atom equals exactly 1 atomic mass unit. So that's the reason there's 12 grams of it for a mole of carbon-12. Right? And that should be carbon-12. Now, if I look at carbon, most of the carbon that exists is in the form of carbon-12, 99% of it. There's just a little bit of it, or less than 1% is in the form of carbon-13. That's the reason this number is not exactly 12.0000. But they chose to do the carbon-12 isotope. In my mind, it would have been much simpler for us to, let's just use the H1, use the lightest atom as a reference. And that happened several hundred years before I was born, so I didn't get the input on it. But what it does is it becomes a reference now, and we can do this conversion factor. And that's all we want to use it. The same way that you could count eggs and go from dozens to number of eggs, that's exactly what we're doing here. We've got a conversion factor, and all we need to do is know the relationship. The same as you know that 1 dozen is equal to 12 of something. Now we know the number of atoms or molecules per mole. And when we do our conversion, we could do it in a way that you could have the number of atoms cancel out on the bottom and give you moles. Or you could set the ratio up. If you knew the number of moles and one number of atoms, you could put number of moles on the bottom and have atoms left on top when they canceled out. And we'll look at examples of both of these. Okay, so when we're doing the conversions and looking things up as a conversion factor, what we do is use the periodic table to calculate the amount of mass associated with 1 mole of something. So an element's molar mass is equal to its mass in grams per a mole of a number of atoms that's equivalent to Avogadro's number. So like I told you on the other examples, 1 mole of chlorine weighs 35.45. 1 mole of Pb is lead, weighs 207.2 grams. Every element, that's the way it adds together.
So a mole can't be broken down.
A mole can, because a mole is actually a large group of number of atoms, 10 to the 23rd of them. Okay, so you can have, if you want to think of, you could split a mole up. You can't say infinitely because eventually you're going to reach a point. So if I had 1 mole of lead, so 1 mole of lead, okay, it would weigh 200, let's see, we said lead weighed 207.2 grams. That equals to Avogadro's number of lead atoms. So I could break it up 10 to the 23rd times till I get down to the level of, if I started with this big chunk of lead, I could keep dividing it to smaller and smaller and smaller. So I finally got to a single lead atom. That's when I can't divide it anymore. It's still the same element. It's just our way of representing that. And what we want to use this as far as our conversion factor to go from mass into number of atoms. Now, something you have to be careful with is that we're starting to learn about what elements are in individual atoms. And we have to understand sometimes we have groups of elements that make molecules. For example, water, just so you understand the difference, water weighs H2O, and if I wanted to calculate its mass per mole, I have to sum together all the elements that exist in that particular molecule. So water has 2 hydrogen atoms that each weigh 1.008, plus the oxygen atom that weighs 16. So that means water weighs 18.02 grams per mole. Okay, because it's a combination of elements. That's the topic for the next chapter, but I just want you to understand that as we're going forward. When we're talking about looking at the periodic table itself, we're looking at individual substances. Now, they can vary in size. So if we look at an example of these guys, these are some different substances and how the amounts of the substances vary. If I look at right at 27 grams of aluminum, that's 1 mole of aluminum. It's Avogadro's number of aluminum atoms. 12.0 grams, 12.01 grams of carbon is 1 mole of carbon atoms. It's Avogadro's number of carbon atoms. If I look at helium, helium's much lighter than either of those. Helium weighs 4.003. So that mass of helium is 1 mole of helium, Avogadro's number of helium atoms. What happens is the lighter an element, the less mass is associated with a mole. And the opposite is true. The heavier an element, the more of them we're going to find in a mole, or the more mass associated with a mole. That's the reason different substances have different densities. We think about lead. One of the things that you know about lead, if you've handled any lead material, lead's heavy. Okay, you get a brick of lead that's the size of a normal brick, you drop it on your foot, you break your foot, because it weighs about 14 pounds. Okay, much, much higher density than what you find in normal materials. Think about lead actually has a little bit higher density than gold. Not much, but they're very close to one another. If you've ever seen any pictures of Fort Knox, all the guys that are walking around, they got these huge shields on their feet. Because if something falls, it's going to crush their feet if all these blocks of gold come falling off. Must be a terrible job, but somebody's got to do it. All right, so what this becomes is simply a conversion factor for us. It's the same thing, dimensional analysis, that we did in the last chapter. We've taken something in one form, or a piece of data that we've collected, and we want to just convert it into another form. So we can use this relationship. So if I know that the certain mass of an element that's listed as its weight in the periodic table equals 1 mole, that can become my conversion factor to convert from grams to moles or moles to grams. And let's look at some examples of that. So when we think about this, we're trying to come up with the tools to do these conversions. So typically what we're going to do first is weigh a mass of sample. We can do that with the balance in the lab. Then we're going to use the conversion factor to convert the moles into the molar mass. And then we're going to use the relationship of Avogadro's number of atoms per mole to find out how many atoms we have. So if you like flowchart type things, we're going to start with a mass. We're going to use the molar mass of the element to find the number of moles of the element. Then we're going to use Avogadro's number to go from the number of moles of the element into the mass of the atom. And typically the way that I like to set these problems up is one continuous problem. If you choose to work these up, set it up, and you work this as one individual problem and get an answer, and then you do the second conversion as a second problem, there's nothing wrong with that. It's the way you're comfortable with doing it. The way I like to do it is because I can follow all my units through. If I don't see the units canceled, that I get atoms left and everything else canceled out, I know I don't have it set up right. Okay, so in dimensional analysis or factor analysis, setting up the units show you how to work the problem. Here's an example. You've got a certain mass of atoms, so or a certain number of moles of atoms. So it's 2.45 moles of copper. That tells us the type of atom. And I'd like to know how many atoms are there. So what I want to do is do just a single step in this, go from the number of moles of copper to the number of atoms of copper. And the relationship between atoms and moles is Avogadro's number. So I'm going to use this as my conversion factor in the calculation. So when you go to work the problem, you write down what you know first. I know the number of moles of copper. Then the relationship is that 1 mole of a substance per Avogadro's number of atoms. And if I look at what would happen to my units, let's see that the moles, top and bottom, would cancel out. I'm left with atoms, and they're copper atoms. So I just need to multiply the two things out, and I get 1.48 times 10 to the 24th copper atoms. Right? And that seems like an extraordinarily large number, but in reality, that's less than a kilogram. Copper weighs 63 grams per mole, so you're talking about a couple hundred grams. Okay, less than a glass of water in terms of mass. Right? Let's look at a couple more. All right, so this is a conceptual one. So this is a clicker question for you. So I want to know which one has more atoms, 10 grams of magnesium or 10 grams of calcium. So answer it on your own. You got those two different elements. So magnesium is Mg, calcium Ca right below it. So you can see their weights. So you got 10 grams of each. Which one has more atoms? And there's no calculation to do. This is just pure conceptual. If you want to prove it to yourself and do the calculation, do it quickly. There's absolutely no need to do a calculation. Okay, a couple more. All right, rolling. Let's see. Varied. Most of you said it was choice B, but a lot of you said they have the same number of atoms. All right, a third of you said that. So if we think about it, I'll go ahead and hit that. Fewer number of you put that. Okay, so if I think about it, I've got 10 grams of this, and I've got 10 grams of this, and a calculator in the floor. So I take those two masses. If I wanted to know how many had more atoms, and I'm going to set the problem up now. So I've got 10 grams of magnesium atoms. And I know the mass is 24.31 grams per mole. So if I divide that out, I don't know, it's 0.3 or something like that, whatever the number is. It's 0.4. It's 0.41 moles, okay, of magnesium. And now if I do a similar comparison of looking at the other element, the calcium, we've got 10 grams of calcium, but now calcium is heavier. It weighs 40.08. Grams of calcium and cancel out. This one's going to be around 0.25 moles of calcium.
It's just this heavier.
Because it's heavier. So, and I told you this on a slide, the heavier something is, it's a couple of slides back. I went over this exact problem, so in fact I'll show you, run back to it. So what happens is, went one too many. Here it is. So when we look at any of these substances, the heavier something is, the fewer grams it's going to have per mole. So down at the bottom of the page, the lighter an atom, the less mass associated with 1 mole. So if you have equal mass, the lighter something means more moles it's going to be there. Okay? It's a conceptual thing that we've got to figure out, but it's just a topic we've got to work on mentally. All right, so let's do a couple of conversions to finish the chapter up. So first one says, what's the mass of a certain number of atoms of iron, Fe? So the way you start these is start with, write down what you know. I've got a certain number of atoms. And again, use the dimensional analysis to make sure your units cancel. So I want to go from number of atoms to the number of moles. So our strategy is going to go from number of atoms to number of moles. And once I find the number of moles, I'm going to be able to convert to mass. So how do I go from number of atoms to the number of moles. What's the relationship? Avogadro's number. So AN, Avogadro's number. Okay? And what's the relationship between the number of moles and mass? So it's the atomic weight. So, and the term we use for it is molar mass. Okay? So MM, molar mass. So first thing I'm going to do is use Avogadro's number, that relationship. It says there's 6.022 times 10 to the 23rd atoms of iron for 1 mole of iron. And next, I've got, if I look at units, that's going to cancel out atoms of iron. Now I'm left with moles. But now I want to go from moles to mass. 1 mole of Fe, iron, weighs what? 55.85 grams. And again, following are my units canceling out. Moles of Fe cancel out. Only thing I'm left with are grams of Fe, which is mass. That tells me I got the problem set up right. 4.65 times 10 to the 22 times 55.85 divided by Avogadro's number. Got something, I can't read it. I've got something. .31 grams of iron.
Would you get 55.8?
Similar mass from the periodic table. Yeah. Okay. It's fine to ask questions. Okay.
So you don't have to do like the exponents for every.
You don't on this one because you only need to do it to, there's 3 significant figures in this term,
Okay.
so the answer is just going to be 3.
Okay.
So you don't have to convert that to scientific notation. Now, if it were something with a bunch of spacing zeros left or right of it, then you would. But if it's a whole number already, leave it. Okay? Question on that? All right, let's do the one at the bottom. The one at the bottom wants to know how many moles are present in this same sample. Actually, that's just a portion of the calculation at the top. So if you took the first step of it, take the number of atoms and use Avogadro's number. You can easily find that out. So take the number of atoms. Is it going to be more than a mole or less than a mole?
Can you just
Just a second, let me come up with my answer and I'll tell you or find out what you're talking about.
So
Okay.
I just took the grams that we got and I multiplied it times 1 mole over the molar mass, just canceled the grams and just did 4.1.
When you were here,
Yeah, I just took that
Yep.
and basically just divided it by the molar mass.
that's doing, you're going, if you knew the number of grams already, okay, so if you were at that point and had done that stage in the calculation, so if you had the number of grams, you could know that there's 55.85 grams of iron per 1 mole of iron, and it gives you the exact same thing. However, you had to know that first. So if you hadn't done, if you want to think of it as this is part A, if you hadn't done part A, you would have to need to go back and do this. But if you look at this portion of it, that is the first step of the problem.
Now my second question is like, in the way I did it, the significant count is different. So like, I only had, oh wait.
Okay, now the key thing on number of significant figures is it's always going to be dictated by the information. Your final result's going to be dictated by the data that you have going into it. And there's 3 sig figs here, and in both cases the answer is going to be 3 significant figures. All right. These take some working, some getting used to. I know they may seem foreign to you. Tomorrow we'll go through the problems at the end of the chapter. I'll work a lot more examples, but I encourage you to start working on the mastering chemistry. Try to finish up as much as 2 as you can and try to get that wiped out. So we're going to go ahead. Hey, I got 10 minutes. I'm using 10 minutes. So we're not going anywhere. We're going to go ahead and start on chapter 3. So I'm not the guy that's going to let you out early. Wrong instructor. All right, so looking at chapter 3, our topics that we're talking about in chapter 3 is now start putting atoms together. We're going to make molecules, compounds, and we're going to start trying to figure out chemical equations to relate those. So we're going to start by looking at hydrogen and oxygen and how it combines to make water. We're going to define some of the different types of chemical bonds. We're going to look at formulas for chemicals and molecular models that we can represent those with. And then when we start looking at those at an atomic view, how we can do representations with those. And then we're going to start looking at first ionic compounds, how we can come up with a formula and convert to the name or vice versa. The important thing that you're going to have to learn this semester is we'll do an experiment in a couple of weeks where you're going to work with copper compounds. You'll have 3 or 4 bottles in the lab that have copper on them. Copper something, and you have to be able to distinguish, is it copper nitrate, copper nitrite, copper hydroxide? You have to be able to look at a formula and go to a name. Okay, it's critical that we be able to do that in chemistry. That's what makes the difference between something being toxic and lethal versus making it being harmless. It's critical we understand naming. We're going to look at molecular compounds and do a similar thing. Molecular species are different than ionic, to go from formula to name and vice versa. How we calculate molar mass, very similar to what we did to individual atoms just a few moments ago, or elements. Now we're going to do it for molecular species. And we're going to look at models of composition, how to figure out what percent of elements something's made out of. How we can determine chemical formulas, some experimental ways of doing that. And we're going to end the chapter with doing some chemical equations and balancing equations, how to write those out, and an introduction to some of the organic compounds. Again, these are problems at the end of the chapter that I'm suggesting that you take a look at in your preparation for the exam. If you can do those, you'll have absolutely no problem with doing my test. Okay. Thing about elements is, even though we've got basically, there's about 90 elements that you can find on the surface of the Earth. There's the extra man-made ones that represent about another 20 or so. But you can combine those into almost an unlimited number of different species. And the species vary on the properties that are different from the elements themselves. Okay, if I look at the example of that, if I look at hydrogen, hydrogen exists as a diatomic, so you never find a hydrogen atom by itself. It's not stable. It binds with itself to be H2. So when I find hydrogen in nature, or isolate it from nature, it's an H2 molecule, 2 of them bound together. It has a boiling point of a minus 253. It's a gas at room temperature, and it's an explosive. And if I look at oxygen, oxygen has a boiling point of a minus 183. It's a gas. It's a necessary component for combustion, and it's found as a diatomic, O2. But when I put those two things together, the results of the water molecule, H2O, are completely different than the 2 elements that put together that made it. Water has a boiling point of 100 degrees, almost a 300-point swing from the average of the other 2. All right? It's a liquid under atmospheric conditions, and we use it to put fires out. You can make small changes, add an atom, take an atom away, and completely change the physical and the chemical properties of something. Okay, one of the ones that we talked about in the previous chapter was the CO2. And the, let me go back and write it on the bottom of this one, is the CO2. and the O2. Okay? Carbon dioxide, you exhale out with every breath of gas that you take. So it's a byproduct of respiration, versus if it has one less carbon atom in it, it's carbon monoxide. What's another name for carbon monoxide? What's a fireman call it? What? It's a silent killer. Okay, 100 people die in the United States every year, carbon monoxide poisoning. And whenever you, especially true with people that have wood-burning stoves, that don't have electrical heat, and that try to tighten their house up so it's not getting cold in the winter, so it doesn't exchange fresh oxygen in it. Exhaust leaks become a problem. And the problem with carbon monoxide poisoning, you just simply go to sleep, and you wake up dead. Okay, it's a problem with truck drivers that drive their trucks and they sleep in the cab. Okay, a lot of truck drivers that drive cross country, the sleeper thing on the back of the truck, that's what they don't use stay in a hotel every night. They get in that camper and go to sleep. But their semi is leaking carbon dioxide underneath the truck, and it leaks that gas. It's a light gas. It floats up. It comes up in the cab. It just builds up and accumulates in there. They go to sleep, and they find them at the truck's been sitting there idling 5 days. They're dead inside. And the reason you know somebody's got carbon monoxide, how do you recognize that somebody's got carbon monoxide poisoning? Purple fingers, purple lips. Okay, they're not getting oxygen. And the way it works is that carbon monoxide binds to the hemoglobin in blood. It keeps oxygen from binding it. And the best thing you do is got to get them on oxygen. You got to get them outside in fresh air, and you got to get them on an oxygen source. That's the way you can save their lives. But they'll act drunk. They're real sleepy. They can't get clear talk. But you look at their fingers. You look at their lips. You literally got an hour to save somebody's life. Yes.
Like if they're up in the cab or whatever, asleep, how would they know they would?
They go to sleep. They personally, unless they've got a carbon dioxide or carbon monoxide detector, you wake up dead. I mean, I'm not being funny about that. That's anybody that's got carbon monoxide poison doesn't know it, because when they're getting it, they lose their senses. That's what makes it the silent killer. You just literally get sleepy and go to sleep, and if it's bad enough, you don't ever wake up from it. And so it can cause, in a minimal case, you recover from it 100%. In a less minimal case, you get brain damage from it, from oxygen depletion, and the worst case scenario is death. But you're talking about hundreds of lives that it takes. If you're in a home that has a gas heater, carbon monoxide sensor is $12 at Walmart. It's something to protect your family. You got children, you're going to have children. That's an investment you make. All right, but changing one atom goes from something that makes it harmless to something that's lethal. Okay, and to give you an idea of the lethality of carbon monoxide, 5 parts per million. 1 million atoms of oxygen and everything, water around you, only 5 of them are carbon dioxide. It's going to start to have a lethal effect on you. 5 out of 1 million. You don't have to be exposed to some of these things a lot. Okay, because the way that they bind is so strong. If we look at water and the way that water combines to hydrogen and oxygen, when you make a molecule or a compound, you fix the composition. This is what Dalton had observed. So he observed that if you looked at water molecules and didn't matter where that water came from, he knew that there was a certain ratio of hydrogen to oxygen atoms. There's 2 hydrogen atoms per 1 oxygen atom, and you know that that's fixed. All right. However, if you have something that's just the elements themselves, if I took a balloon and I can put hydrogen in it, oxygen in it, and I can release those gases at any ratio, I can change the composition. So if it's in the element form, I can have H2 and O2 at any composition I wanted to have. And you could ignite that balloon. If it ignited, H2 plus O2 form water. And it releases a lot of energy out today. That's part of the hydrogen environment. We'll talk about that as we go forward. All right, start studying. Get that master's in chemistry done. See you tomorrow.